Hello, Internet. This is your captain speaking, Lester Nare. I'm joined by my co-host and our resident PhD, Dr. Krishna Chowdhury. This is From First Principles. We have a great episode this week. We are going to touch on first, Beetlejuice. Found a companion, but this is not Love Island. A great story about a stellar companionship. Second story, atom scale images of atoms vibrating. We've seen atoms doing the Harlem Shake. What does it mean? What are the implications? Story number 3, high energy cosmic rays. We're talking too fast and too furious. Fourth story, navigating the stars using a camera. We've figured out an interstellar Google Maps, or have we? And lastly, we'll end with our mystery box, which is Krishna's story of the day. How are you, good sir?
I'm doing well. Second episode.
I'm very excited about this.
Yeah.
First one went well. Maybe we'll do a third one.
Yeah. Yeah.
So we'll start with our first story. Interestingly, it got all the way to CNN. Which is, usually when news gets to there, it's a little bit dicey.
This one's not fake.
Okay.
This one is not fake.
So the title on the story is Beetlejuice, one of the most familiar stars in the sky, may have a hidden companion star orbiting it. Astronomers have observed what they believe to be a never-before-seen companion star orbiting Betelgeuse, a pulsating red supergiant star in the shoulder of the Orion constellation.
That's right.
Why? What exactly is happening here? Why does it matter?
Yeah.
And does the galaxy lie on Orion's belt?
The galaxy is not on Orion's belt. Orion's belt is actually just in the galaxy itself, so it's the other way around. Betelgeuse is just one of my favorite stars. And so whenever anything happens with Betelgeuse, I get very excited. This might not matter in the grand scheme of things to human beings, but I still think it's an extremely cool observation that we've made about my favorite star. So, you know what? Tough. If you guys don't like Betelgeuse, whatever. Just go see Orion, and you'll see him on the top right shoulder. So Betelgeuse makes up the top right shoulder. It's unmistakable. It's red. It looks like Mars, except it's blinking, so you know it's a star.
Okay.
Mars is about the same brightness, but it doesn't blink because it's closer to Earth, so it's a little bit bigger. It's like Mars is kind of like a circle, whereas Betelgeuse is 700 light years away, so it's literally a point, and so it twinkles a little bit.
That's a nice little short drive through the interstellar vacuum.
Honestly, it's not that far. 700 light years in the grand scheme of things is not that far. It's actually the closest red supergiant to Earth.
So when you say supergiant, it's a star.
It's a star.
So a lot of people will think, it's like a bigger Jupiter, but that's not true.
No. This thing is it's nice that you mentioned Jupiter. So this star is so big that if you were to put it where the sun is, it would be as big as Jupiter's orbit.
Oh, wow.
Yes.
So it would be like this all the way past the asteroid.
It would swallow Jupiter. Now you see why it's my favorite star. It's like, it's an amazing star. It's this red supergiant. This thing's only 10 million years old. Okay. So it's like the sun is 5 billion years old.
Okay.
And the sun is going to become a red giant, but not a supergiant.
Oh, so it's
dying.
It's on the path.
This thing is dying. It used to be a blue massive star, and then it ran out of oxygen because one of the cool things about stars is like the bigger you are, the shorter your lifespan. It's kind of like you party too hard and then you're just like fucked.
Yeah,
right?
Live free and die hard.
Yes, exactly.
Yep.
Stars do that exactly.
Okay.
Like the bigger you are, the faster you deplete the hydrogen.
That gives you life.
Right? That gives you life. And then now you ran out of hydrogen. Now you got to start burning helium. Once you run out of helium, now you got to start burning carbon and nitrogen. Once you start running out of that, you swell up, and then things are bad. Fair. So this thing is in its last legs.
Okay.
But it's this massive star, 700 light years away, 700 times the radius of the sun, and it does a lot of really cool things. Okay. One of the cool things it does is every I think it's every 400 days, it has a cycle where it like dims and it gets brighter, and it dims and it gets brighter. Now that's okay.
That's pretty close to the Earth's.
Yeah, it is.
Cycle.
Like 365, 400. Yeah, right. It dims, it gets brighter. That's like okay for red supergiants because
Okay.
things do that. Okay?
Okay.
A lot of these stars do that.
Okay.
If you look at other red supergiants that are farther away, they'll do the same thing.
So they don't stay at the static.
No, they're called variable stars, and they're actually very important for like that's actually super important for like fundamental science reasons because that tells us how far stuff is by looking at the frequency of this. It tells us how bright they really are, and then you can tell, okay, well, I know how bright it really is because it's oscillating at this frequency,
Right.
but I see it as this bright. So why is it this bright when it should be this bright? Oh, it's because it's this far away. And you can tell the distance to stars. So variable stars are extremely important for fundamental science in terms of like calibrating that. Edwin Hubble did the first kind of survey of that out in Mount Hubble.
Oh yeah.
Not Mount Hubble, Mount Wilson,
Yeah.
right in the outskirts of LA.
This is the same thing you were telling me about the other day, I think, with like how we use quasars for time and for like because they're so consistent.
Yeah, because they're so far away and so consistent, you can use them to chart like 360 degree rotation of the Earth. In this case, it's like because these guys are so consistent in the way that they vibrate and how bright they are, we can use them to chart distances.
That makes
as
sense.
as we go out.
That makes sense.
Yeah. Anyway, so 400 days it does this cycle. That's fine.
Yep.
But every 6 years, it does another cycle. So there's like a 400-day cycle.
Yeah.
And on top of that, there's this slower 6-year cycle. You see what I'm saying?
Yeah.
There's like a slower
Yeah.
oscillation on top of this faster oscillation.
Yeah.
And that slower oscillation is 6 years. And that one's weird.
Okay.
Okay. So people thought, okay, that's weird. 6 years is kind of long. They thought that maybe there's another star that is wobbling it. Okay.
That would be impacting.
That would be impacting this that would be orbiting it every 6 years.
Yep.
Okay. But it's been incredibly hard to see because Betelgeuse is so massive, right? It's the size of Jupiter's orbit. So like it's like to try and image the other star, it's like you got this one dancing partner that's like outshining you in every form of the word.
This is like I don't think people understand the scale of what you're talking about.
Yeah.
Like this thing is so incredibly large. It's hard to even.
Yeah, it's hard to even. It's so incredibly large and so incredibly bright because it's large.
Right.
Right. That like when we point a telescope at it, all you're gonna see is it. You're not gonna see the other guy.
Right. That's right.
That's like right next to it, like 4 Earth orbits away.
Because it's basically gets sort of engulfed.
Yeah.
In the supergiant. I mean, this sounds very similar to what we talked about last episode about Earth's 1 millisecond shift in its orbit time, which was partly because of we don't know, but other objects interacting with Earth. So similarly, you're saying that this supergiant is having this companion that is what is impacting and creating this 6-year cycle in addition to this 400-day cycle.
Yes, exactly.
Okay.
Right?
Okay.
And so like the idea is like you have this interaction and we see it in the brightness of Betelgeuse, but we want to actually see the thing, right?
Yeah,
we want to see its partner.
Right.
So that becomes incredibly hard.
Wait, just really quick, because you're saying we can measure and then make a hypothesis that is being impacted by this thing, but we've not made a direct observation.
Yes. Because when you point your telescope at it, all you see is a single point of light.
Right.
You see a single point of light, and that light's brightness is going up and down every 6 years. Right? Now, what we think is that there are 2 points of light.
Right.
But how do we resolve that 2 points of light?
Got it.
Because I actually did the calculation. Okay. This thing, it turns out, this thing is about 4 Earth astronomical units. So 4 Earth orbits away from its star.
Yep.
Okay.
Yep.
And it's got about 4% the brightness of Betelgeuse, this new star.
Okay.
Okay.
So it's very dim in comparison.
Yeah. And this thing is 700 light years away. So that's the same as if somebody in New York City went on to the top of the Empire State Building and put up 2 iPhones with their flashlights.
Yeah.
They put them right next to each other, right? You hold 2 iPhones, you put the 2 flashlights, right? Imaging Betelgeuse and its companion, it's as hard as imaging 2 flashlights on 2 iPhones right next to each other on the Empire State Building from Los Angeles. right? Imagine trying to take a picture of that from LA.
I mean, the Samsung Galaxies are pretty good.
Hey,
You know, right? The Xiaomi phones are also pretty good.
yeah.
But I don't believe.
I don't think they.
I don't think if I was at Spire 73 in downtown Los Angeles, the highest open air bar in the Western Hemisphere, at least as of 2 years ago.
It's a great bar.
And I pointed it at New York.
Yeah. Well, the Earth would be in the way because the Earth is round. But let's assume it's flat. Let's assume it's flat. Fine.
Don't get in the comments.
Don't clip this. Don't do the thing. Okay. Yeah. But
I think I don't even know that I would get to the east side.
No, yeah, you wouldn't. Yeah, like even if there was a vacuum,
right,
you wouldn't be able to resolve these things.
Yes.
It would just, if you were lucky enough to even see the two iPhones, they would be like one dot.
This is actually really helpful context for understanding the scale of the challenge
that
we're solving
exactly.
with these experiments and these tools.
Yeah. So it's an incredible feat that we could do this, and the image that they produced is amazing. They used the Gemini not the Gemini Space Telescope. Sorry, they used the Gemini Telescope in Hawaii.
Yep.
That's at the peak of Mauna Kea in the Big Island of Hawaii. It's a beautiful, massive telescope.
Hawaii.
Yeah, it's one of the best parts of Hawaii is the fact that they have these incredible astronomical observatories that are like unmatched in the Northern Hemisphere.
Which makes it because no light pollution.
Yeah, no light pollution. It's like perfectly poised, super high altitude in the middle of the ocean, 13,000 feet above sea level,
which is 4,000 feet lower than the Atacama, because the Atacama one is about 17,000. So
and Atacama is basically a bunch of Europeans. Like they've colonized the shit out of Chile's high desert, for astronomy. But it's for astronomy, so you know.
I will make a small caveat. We do respect the desires of the locals in Hawaii and that their lands are theirs. And so this is not a claim to that land as being property of the globe. However, there is a lot of value for all of us in being able to have these tools in particular locations. Yeah. And we are grateful to the people of Hawaii for that.
Yes, we're incredibly grateful for the people of Hawaii for lending their land to give us these tools to explore what really is the final frontier. Right. Like I don't want to digress too much, but it's like in the cultures, it's like exploring the unknown, right? Yeah. Exploring the oceans was how they got to Hawaii. And now it's like they're exploring the vast ocean of space. Right. It's incredibly romantic to me that like it's, Hawaii is the spot where all
this is happening.
Yeah.
I will say that my wife wanted me to propose when we went to Hawaii and we're looking at the observatories. I did not get the memo, so that did not go over well.
Oh, dude.
However, we are still here today, so
yeah, you're good.
It could have been worse.
It could have been worse. Yeah,
it could have been worse.
Yeah. So I proposed on Mount Wilson.
Oh, really?
Yeah. So I don't think she got the memo, but I had the memo.
This is great. So the real story here is we sort of this connection between measurement and direct observation.
Yeah.
Right. Or measurement.
It's like a hypothesis, right? We're doing the scientific method where we see this thing and we exhaust all the other possibilities and we're like, well, it's got to be like a companion. Yep. And then we're like, okay, how do we measure this thing? And so we point this Gemini North Telescope to it. Yep. And we also use this thing called speckle imaging, which was actually developed at UCLA. A lot of it was developed at UCLA to try and image the center of the galaxy to see those beautiful star trails around the black hole center that won Andrea Ghez the Nobel Prize very recently. It was actually like on the floor above my PhD lab. I was on the 5th floor, and then the 6th floor was basically all an imaging lab that was trying to make imaging these tiny little things possible, right? And they use that to prove the supermassive black hole. But in this case, what they used, and speckle imaging is basically like you take a bunch of really fast images. Okay. You take a bunch of really fast images and then you average them together. The reason why you're doing this is you treat each image as an independent sample. So instead of like taking a long exposure where like the atmosphere is in the way and so you get a lot of blurring, what you do is take a bunch and then you mess around with each image and average it in just the right way that you can start resolving like incredible detail.
That's very
right, because you want high resolution and high contrast.
Right, which you can't get on the long exposure.
Yes.
You can't get with a short exposure, but high volume
yes,
averaged.
Exactly. So that's called speckle imaging. And some of these exposures, they're like extremely short. They're like 14 milliseconds. 14 milliseconds.
This is, oh my goodness.
Right? And you're taking like thousands of these, and then you're averaging them together. And finally, you get this beautiful picture of Betelgeuse and its little companion. The little companion is like 4% as bright as Betelgeuse, so obviously we weren't seeing it before.
The little bro. This is little bro.
This little bro, and
the little giant.
And unfortunately, it is not a nice relationship. This is not.
Oh, okay. So
this is not a Disney happy ending.
I referenced Love Island earlier because I thought companion is usually
mate,
referenced
it's
in
not
a way
it's not going to end well.
I imagine the supergiant
Yeah.
is going to be engulfing
Yes.
the companion.
Yes.
We don't support a
that boy's this 4%.
Yeah.
The size. It's not. It's like I think in the next 10,000 years, it's gonna be gone.
I'm so happy we're gonna be able to see that in our lifetime.
Yeah, it's gonna be pretty cool.
That's incredible.
One last thing.
Yes.
Sorry.
No. Go ahead.
Oh, I was gonna say one last thing that I think is very nicely done by the astronomers. Right. When you discover a new object, you tend to get to name it.
Okay.
Okay.
Mm-hmm.
So Betelgeuse. Mm-hmm. Betelgeuse is an interesting name.
Spelled Betelgeuse.
Yes.
Not like the Beetlejuice we know. It's like a French.
Yes, this is a weird Beetlejuice. It's actually an Arabic name. Okay. It was named by the Arabs back when Europe was in the Dark Ages, and Arabia was where scientific learning and all of that was happening.
They don't teach us that in school.
No, but
they deliberately ignore centuries.
Yeah, like algebra is from algebra. Algorithm is like named after an Arabic word. Anyways, Betelgeuse means the hand of a giant.
Okay. Because
like it's on his shoulder.
Yep.
Right.
Okay.
And they probably inherited those constellations from the Greeks.
Got it.
Right. And Eljuice means giant in Arabic. Mm-hmm. So they stuck to that theme, and they're naming this new star Siwadha, which means bracelet.
Okay.
It's like bracelet on the hand of a giant. I thought that's kind of cool. I don't know.
Look, I appreciate that you can both be technical and creative at the same time.
Yeah. And I think it's nice,
So although the ending of the story may not be the most happy, this is not a Disney movie, as you said.
No.
It is another great example of, again, just the incredible genius of so many of the human beings around us. And so I think now we talked about really, really big stuff.
Yes. This is that star was the size of Jupiter.
Which is
the orbit, not the planet, the orbit of Jupiter, like the sun, Jupiter. Yeah.
So now we're going to go in the opposite direction.
Yeah.
So the headline on our second story here is first direct images reveal atomic thermal vibrations in quantum materials.
That's right.
And then the byline goes, researchers investigating atomic scale phenomena impacting next generation electronic and quantum devices have captured the first microscopy images of atomic thermal vibrations, revealing a new type of motion that could reshape the design of quantum technologies and ultra-thin electronics. So the way I described it was we've seen atoms do the Harlem Shake.
Mm-hmm.
So, but it seems like the key idea here is it's an imaging feat of something really, really, really small, and the thing that we imaged that was really, really, really small was doing a little shimmy.
Yes.
So how do we go from this really small thing vibrating to ultra thin electronics?
Yes. Well, first we got to understand what is the thing that we imaged, okay?
Yes.
So for that, have you ever heard of moire patterns? Moire.
Yes, like with the accent on
moire. Yeah,
well, that's so moire.
You might have seen it. Yeah, it's kind of like that.
Do you know what it is? In film, you get it on your imaging, like in particular situations. They call it's like a moire effect.
Yes, yes, exactly.
And so yes, but what does that have to
do?
Right,
like I get it. You can get it all the time if you take your phone and then if I were to take my phone and then take a photo of your LCD screen,
it's got the
right, and then I zoom in on the like if you've ever taken a photo with your phone of like a screen,
Yep.
and then you zoomed in on the screen, you're gonna get these like weird like netty patterns.
Yes.
You know.
Yes.
And why is that happening? That's because there's a pattern on the LCD screen. Okay. So because the LCD screen is a bunch of pixels, so there's a regular pattern on there, and then your phone, the way it's displaying it, has another pattern, right? So what you're doing is you've got these two patterns. You've got these two patterns that are overlapping.
Yeah.
And when you do that, you get these giant patterns. Like there's a third bigger pattern
from the sort of the amalgamation
exactly
of those two small
ones.
ones.
So what you need is like two small patterns, and then you slightly offset it, and you'll get these like nice like looking bigger patterns.
I think some film people would disagree with you about the characterization of nice.
Yes.
However,
I don't know if it's nice. From a quantum materials perspective, it is quite nice.
This is okay.
Okay.
So I do know what you're talking about.
Yeah.
And it's basically it's an interference pattern.
Yes, it's an interference pattern between two regular 2D patterns, right? There's like two patterns in 2D. We're making them interfere slightly. It can't be like completely.
Got it.
It's got to be like just slightly a little bit off, and then you'll get these like long range patterns, right? The smaller the difference between them, the longer the range, right?
Okay. Yep.
And so what you can do now is you can create these like silicon heterostructures. So you can have these like materials that are made out of silicon, and then you like put some other stuff in it.
Yep.
Right?
Like chips.
Yes. I mean, chips are exactly like silicon, and I think boron or like some other kind of element on top. But in this case, what we're really trying to do is we're trying to measure the properties of tiny, like extremely thin silicon heterostructures. Okay. Hetero just means different. So you're putting some other stuff in there. You get the silicon, and usually this structure forms a kind of 2D lattice, right? A 2D grid.
Yeah.
Now, if you stack two on top,
Like graph paper.
yes. If you stack two on top, then there's going to be some kind of defect, right? Usually, and that's going to cause these moire patterns because you have a lattice of like atoms, and then you have another lattice of atoms. These lattices are like nanometers apart. So like, tens of atoms apart. And then there's going to be some defects. So you get these moire patterns within the atomic structure of the thing that you're trying to study.
What it makes me think of is when I was in math class and I would have my notebook and I would have graph paper, and if I would remove the paper slightly so it wasn't perfectly aligned with the page below it, you could kind of see a little bit of the
you can exactly see a moire pattern.
Right. Like is it loosely in a simplified way a similar concept?
I mean, no, it's literally that concept.
Okay.
Yeah, no, it's not even loosely. It's literally that. Right? You got a grid on top, and then it's a little bit off, and you get a little pattern.
Okay.
Right?
Got it.
So
these in this pattern, we're trying to image this really, really small structure. That has these patterns present.
Yes. And so these patterns, like these structures, right? These like thin structures with like these interacting sheets that have this like long periodicity in space. They're really important for things like superconductivity, heat conduction studies, new materials, like stuff of the future.
The metamaterials.
Right? Like the stuff that we want to make in the future. We want to make it cheaply. We want to make it at an industrial scale. But in order to do that, first we need to understand physically what is going on.
So as an analogy, we have a Lego block that's 8 by 8.
Yeah.
That's the level at which we can like engineer.
Yeah.
We're trying to get down to a Lego block that's 1 by 1. Like
in some sense,
and a smaller, and understanding of
the Lego blocks
at that scale.
At that scale, and at that like even you're trying to also make the Lego block like incredibly cold, so that you can understand the physics at the basic level.
I gotcha.
Right,
Yep.
And you're trying to understand like the atoms within the Lego block in some sense, right, and like how the Lego block stretches and shears and squishes. That way, when you make a bigger thing, you have a better handle on everything.
You understand all of the sort of derivative outcomes that will happen because of effects at this really, 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 really small scale.
Yes, yeah. And so you've got these like moire patterns, right?
Yep.
And it turns out these patterns will actually move around. Okay?
Okay, hold on.
Yeah. Because the defect, right? The defect that creates this pattern is going to move because the temperature is not zero.
Oh,
So
right.
because temperature is not zero, there's going to be some wiggling going on in the lattice. And because there's some wiggling going on in the lattice, the pattern itself is going to move, and it's going to be constantly shifting.
Yep.
So understanding how this thing shifts, what's the physics of that, is incredibly powerful and incredibly needed for understanding like how these 2D heterostructures work. And that's what these guys did. They're from the University of Maryland. They did something called electron ptychography. That's ptychography. Okay. Tycho means like to fold in Greek. Okay. And it's a new form of like electron microscopy basically.
Okay.
But it's like halfway between X-ray crystallography and electron microscopy. So electron microscopy is the idea of like when we think microscope, we think like a light microscope, right? Like the stuff in your bio labs.
The stuff we did in 8th grade.
Yeah.
We're looking at frog legs.
Where it's like okay, you're using visible light. You've got a traditional lens, and then you try to like see stuff. Now, visible light has a size, like the wavelength of visible light, the stuff that's in these lights, of about 400 to 700 nanometers. Okay. So the wave has a spatial resolution of 400 to 700 nanometers, which means you can't see stuff smaller than that, right?
range.
If you've ever been to the ocean, if there's a tiny little island and the waves are like 10 meters apart and the island is like a meter, the waves don't give a fuck. They're just going to go through, right? But if the island is massive and the waves are small, then the waves bend around it, and that's when you can actually resolve stuff. Okay, so visible light is not going to work. Because visible light, the smallest you can go is like 400 nanometers, right?
This is why when people talk about like signals intelligence gathering or these kind of detection platforms, right?
Yeah.
You have optical, you have radio, you have infrared, and the point there is that range is at different.
Yeah, it tells you the resolution of the stuff, and there's like some atmospheric effects in the stuff that you're talking about.
Sure.
But like for example, with radio. Like if you take like a long wave radio image of something and the something is like the size of a size of you, then you're not going to resolve anything, right? Because the radio wave is massive, right? So what are you doing?
What are you doing? No, okay. So the scale of this stuff just continues to always blow my mind. Yeah, that we can even.
Yeah, I haven't even told you the resolution that these guys got. Okay, so but here's the other thing. Okay. So I told you, right, like usually you use light and light microscope in the bio lab, but now like biologists increasingly they use electron microscopes because of quantum mechanics. Electrons have wave-like properties, the wavelength of electrons is around X-rays. It's extremely small.
Got it.
So if you shoot electrons through stuff, through a sample, then you can resolve at the wavelength of electrons. Right, because they're the same in quantum mechanics, and so now you can like resolve down to like the angstrom level, right? So but that's not good enough.
That's still not good enough.
The one angstrom is the size of a hydrogen atom, and that's not good enough for these guys. Okay, because in order to see these thermal vibrations,
were they Chinese?
No, University of Maryland.
But were the scientists Chinese?
It might be. Yeah. They might be.
Immigration matters. That's all.
Yeah. They might be, but I mean, I don't know the citizenship of them and things like that, right?
That's fair.
But if they're U.S. citizens, then yeah, we gotta keep them right here.
This is important stuff.
This is important stuff.
We want the ultra thin.
Yes. We want the ultra thin electronics.
I want the self-driving car that can jump over a puddle.
Exactly.
Anyway.
Yeah. So these guys, it wasn't good enough for them, an angstrom, right? And so what they did was with electron ptychography, what you can do, and this only happens with periodic materials. So with like stuff that looks like graph paper, what you can do is you can shoot electrons at something that looks like graph paper, and you're going to get what's called a diffraction pattern. Okay. Right, because like all of the electrons are going to interfere because of the lattice structure, because of the periodic structure of stuff. So you're gonna get like one lattice pattern. Now what you're going to do is move the samples up. And then do it again. And then move the sample up and do it again. And because the sample itself is periodic, right? The fact that you're moving this is going to give you higher resolution on the image that comes at the end. That's the genius of electron ptychography.
So
right? Like it's the fact that this thing is graph paper. If this thing wasn't graph paper, then you'd be just taking like photos of like different parts of the stuff. But because it's graph paper, I move it up. It's the same thing
from before.
Right? And so now I can use the spatial invariance to nail down my resolution in space. And then I get down to 15 picometers, which is 0.15 angstroms. So it's 15% the size of a hydrogen atom. And that's the images that you're seeing there in that article, right? Like those individual dots, those are individual atoms, right? Like that's a single atom in a lattice. And then there's a bunch. Like each dot is an atom. It's incredible. Like the image is incredible.
The image we're looking at right now kind of looks like when you were a kid and you go up to the TV really, really, really close and you can see each of the individual pixels
like
on the TV.
Yeah.
Just for the
back when it was
listeners.
we had like the electron tubes.
Yes. Yeah. The vacuum tube whatever.
Yeah.
I'm at kind of a loss of words.
Because we're seeing like the nature of the material in itself, it's incredible.
Isn't this like a level at which things start to get a little weird? Like we're getting close.
I mean, no, things are already getting weird.
Things are already weird.
This is at this level, it's already.
When you're looking at it, it's a little.
Now you're starting to get into like Heisenberg uncertainty principle style stuff.
Okay.
Yeah.
This is incredible. Okay, and so I think one shout out to U.S. academic research institutions.
Yes. Shout out to how we import the international talent
in the world.
You're
still going to get funding. Don't worry about it. We got enough money flowing in. Come here, help us build and discover incredible. It's really hard to for a layman to internalize, because I think the delta between my everyday understanding of science as someone who comes from a family of scientists, and then like people who just don't have that conversational context or exposure to the information, don't really understand how thorough, robust, and outrageous the process is to do the things we talk about that then make it into papers.
Yeah, no, it's like 0.15 the size of a hydrogen atom. Right, that's the resolution. That's the size of the pixel that we're imaging this thing.
It's also reproducible, so there's no belief going on here.
No, somebody else can do exactly what they did
and be like,
and you know what'll probably happen is like whoever's the competitor is gonna do what they did, make some tweak, make it better, and be like, well, I made it better. Yeah, like that's how scientists are. We're petty as fuck, dude. Yeah.
That second story, I'm gonna have to take a second to.
It's crazy because the more we understand these kinds of materials, right, the closer we are to these next generation materials. I mean, superconductivity. It could be like there's also some talk about like creating like quantum computing using these these 2D materials. Right. Like maybe the vibrations in these materials can be our 0 and 1 for the quantum computer that we want to make. Yeah. I mean that may be a little bit
caveats.
Like there's a lot more work there. Yeah. But like understanding 2D materials that are this thin are incredibly important for like quantum sensing, which is very important.
We can't get to the next step until we get to the first step.
Yeah.
And the first step is knowing how stuff at this level operates.
Yeah, and this is also the first time that electron ptychography has been used to study this kind of material, right? So the big thing is like using this experimental method, which has been used before,
right?
But now it's like being used for this kind of stuff, applying to these Mare patterns, right, in these like 2D defect structures.
This is, I think.
So it opens up like, okay, what else can we do with electron ptychography?
There's two big, like sort of key insights here. One is that the methodology applied to this use case bears fruit, and two, the fruit that we got is delicious.
Yeah,
it's ripe.
It is nice,
juicy, and we can get more of it. And okay, this is great. So we started off really big, then we went
really small.
Way small.
Yeah,
really a little small. Whiplash. We're gonna stay small for our third story. Let's just jump into it. So in Antarctica, we have, would you call it? And it's not an observatory. We have a facility.
Yeah.
Called.
It kind of is an observatory,
but not the way.
People think. Yeah.
Right.
Yeah.
So IceCube, not NWA IceCube.
Yeah.
There's no space in between the two words. neutrino search sets first constraints on proton fraction of ultra high energy cosmic rays. Neutrinos are subatomic particles with no charge and very little mass that are known to weakly interact with other matter in the universe. Due to their weak interactions with other particles, these particles are notoriously difficult to detect. However, it seems like we may be on the path here. And so this is where we're talking about too fast, too furious, because we're dealing with ultra high energy energy cosmic rays.
Yeah.
I mean, this sounds both dangerous and exciting.
Yeah, it's incredibly exciting because it's a part of physics that like seriously people don't know.
Okay.
How you get something so fast, so furious.
Because what we're saying is this is after Fast 5. So for the Fast and Furious franchise watchers who are familiar, everything up to Fast 5 was, generally speaking, realistic. Everyone could be like, oh, I can understand how a car goes that fast. I can understand da-da-da.
Makes sense.
As soon as they started flying off of cliffs and being in space with cars, then the question, all right, how you do that?
How you do that?
And so
that's what physicists are asking. How you do that?
For these ultra high energy cosmic rays, the shtick seems to be, in some cases, they're moving so fast that we don't have an idea of how they were able to achieve that level of speed.
Yes.
Is that
That's
accurate?
exactly right. Yeah. So let me tell you first about cosmic rays.
Okay.
Cosmic rays are basically particles that come from outside the Earth.
Okay.
And they're like big particles. Big particles, I mean like like immigrating particles from way out there. Okay? These can be something as light as a proton.
Okay.
To something as big as like a gold nucleus.
Okay.
Right? A gold nucleus is like hundreds of protons.
Okay.
Right? So and they're incredibly fast. They're going very close to the speed of light. Okay? Now, usually what we do is we measure the energy of these particles using something called the electron volt, which is how much energy it takes to move an electron across one voltage of electric potential. It's just a way of measuring. Energy at the particle level. To give you some idea of what that means, like CERN, which is the big particle collider.
It's where apparently European scientists are interacting with interdimensional beings, according to the internet.
Oh, that's new. I should talk to some of my friends who work there and see if they can put us in touch.
I know you know.
That'd be a great guest on this podcast, interdimensional beings. Tell me, sir, do you know where cosmic rays come from? Was that you? Was that you?
Well, actually, but CERN is this. It's the same thing as the LHC.
Yeah, it's the Large Hadron Collider. So the Large Hadron Collider, this massive particle collider that builds the biggest.
2 miles.
No, it's like 13 miles.
Oh,
it's across two countries.
Yeah.
Like France and Switzerland share a border, and it goes underneath that border. It's that big.
Okay.
It's what created the God particle, the Higgs boson. Incredibly high energy, some of the highest energies that we can pack into a small space, into individual particles. The proton beams that go around CERN right now are at 6 TeV, which is 6 times 10 to the 12. So 6 with 12 zeros electron volts. Okay,
I want that in my bank account.
Yeah, like that's a lot of electron volts packed into a single proton. Right. An electron volt is how much energy you would need to take one electron up 1 volt.
Right. And
this is
all of that
6 times 10 to the 12 into a single particle. Okay, that's a lot of energy, but at least we can imagine how to make it. Okay.
Yeah.
And you might have seen all the headlines of being like, we're accessing the beginning of the universe, right? And we are, because like at those energies, we're accessing the beginning of space and time itself, right? We're getting as close to the Big Bang as we possibly can.
Right.
Okay. So 10 to the 12 electron volts is like, it's pretty nice.
We can do it. We can create that. We can understand it.
And we're good to go.
And we have all the frameworks.
Yeah, we're good to go.
We know the tactics and the
We're good
strategy.
to go. Yeah. And then came the biggest cosmic ray of all time.
I think I remember this.
Okay, it was called the OMG particle, the oh my god particle.
Oh my.
Yeah,
God.
it was discovered in Utah randomly. I mean, not randomly. Obviously, a bunch of physicists had these cosmic ray detectors. It had 10 to the 20 electron volts in a single particle. That's how they detected 10 to the 20, which is a million times the energy of the proton in the LHC.
Okay.
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 So now we're like, okay, what?
Hold on a second. Hold up. Wait
Hold
a
up.
minute.
How do you pack so much energy
into
a single particle?
You know what this reminds me of, and it's totally unrelated, but our discussion about vacuum energy, which has a similar question of how can there actually be that much energy?
Yeah.
It's unrelated, but just the level of
the level of awe about like how does this even happen?
Right.
Like let me give you some stats because I did some calculations about like what that would mean. Okay, so 10 to the 20 electron volts in a single particle. This is the oh my god particle. If we wanted to see how fast it was going in terms of the speed of light, because nothing can go faster than the speed of light, but the closer you get to the speed of light, the higher your energy is, right? This thing had 0.999999999 with 24 nines before other numbers show up.
Oh my god.
In terms of like, so 0.999, 24 nines, and then like 5 fours, like C times the speed of light. Okay? Going that fast, if it originated oh
my god,
1.5 billion light years away,
okay,
right? Then because of relativity, from our reference frame, it would basically take 1.5 billion years to get here, right? But because of time dilation in relativity, the faster you move, the slower your clock goes.
Yeah.
From that particle's
from
perspective,
the observer's perspective,
from the particle's perspective, it would only have lived 1.5 days. To us,
get out of here.
To us, it's 1.5 billion years, but to the whatever particle it was just like, 1.5 days. I'm here on Earth. Hey, it's Utah.
I was gonna say it takes us that long to get to like Texas from here.
Yeah. Mate, like so. The other thing, it would take a photon 250,000 years. So like if it was in a race with a photon, right? So there's our particle, the OMG particle, and then there's a photon. If these two were in a race, it would take the photon 250,000 years to get a 1 centimeter lead on this guy. That's what's happening here, right? That's where we're like, okay, like this is incredibly fast. What makes a single particle that is massive? It's trivial for photons to move that fast because they're massless.
Right.
But this is something that has mass, so it requires work to actually accelerate it, right?
Yeah. No, I mean,
like you can't like photons. You just create it, it moves because it's massless.
We're not concerned about the speed of a photon because it has no mass, and so of course it can move at incredibly high speeds.
Yeah. By relativity, it's like trivial. But like this thing, it has stuff in it. And the stuff is it has a rest mass.
Its rest mass is also huge.
Yes.
Comparatively.
Yeah, I mean it's a proton compared to a photon, which is 0. Yeah, it's at least a proton, right? It could be a higher nuclei.
Yes, right. But it's at least that.
Yeah. And all of these calculations are with the least.
This is like I can't.
So yeah, and you start wondering, okay, like where do these big cosmic rays come from? Okay, you might think, okay, it's like supernova, right? Like supernova, it's a massive star, it blows up, and then it like sprays a bunch of like mass like these particles with massive energies. Like fine,
pictures.
No, but those cosmic rays should not have 10 to the 20. Okay, like for a supernova to have 10 to the 20. Is like it's the star is too big to have
even
like
existed in the first
place.
Yeah.
It's like how do right? And then it's like so there's some theories that suggest that it's a particle that's been like forming from the great beginning of the universe, and then it's interacting with the cosmic microwave background, which is just the background like light of the universe that's left over from the Big Bang, and that light from the universe is bombarding it in just a way to like accelerate it. But like that seems like crazy, right?
I don't like that explanation.
The idea is we need more data about this. Okay, so that's where a neutrino observatory like IceCube comes in. Okay. So IceCube was started by the University of Wisconsin, Madison. One of the great things about America is that like our flagship state institutions are just doing like ridiculous research that like other countries would be jealous of, but ours is like, no, Wisconsin got this.
This is S tier basic research.
No, this is like Wisconsin got this. Like all those like alcoholics over there are like, you know what?
Jesus.
We're also gonna make the greatest neutrino observatory in the world.
Shout out UW Madison, because this is
it's incredible. No, so this IceCube observatory is like one of my favorite things that humans have done. Okay, we basically went to Antarctica. We're like, we got all this ice.
Yep.
What do we do with it? So they bored like this like 1 to 2 mile deep tunnels into the ice. So the area of the observatory is about 1 square kilometer. It's like a few city blocks. And then they bored a bunch of tunnels that are 1 to 2 miles deep. And in it, they put photomultiplier tubes, which are basically like light detectors. Okay? You can think of them as light detectors. Now, here's what happens. Cosmic ray comes in. Okay? Slams into the ice. Okay? When it slams into the ice, all of that energy, it's gonna hit one of the water molecules or something like that. It's gonna spray a bunch of neutrinos everywhere, right? Because all of that energy has got to go somewhere. So it's going to spray all these neutrinos. And then those neutrinos are going to bump into other water molecules and so on and so forth. Pretty soon what's going to happen is there's going to be a charged particle, either a proton or an electron, that's going to move through the ice at faster than the speed of light in ice. Think about that for a second.
I don't get it.
Yeah. The speed limit of the universe is the speed of light in a vacuum.
Right.
But light moves slower in stuff. Right, light moves a little bit slower in air. It moves hella slower in water. It moves the slowest in diamond, which is what gives it its sparkle. Okay. In ice, it moves pretty slow. Right, it's got the water has this crystalline structure that's slowing down the water.
That scares me, because if that's the case, then what you're about to say is even crazier.
Yeah. So when this cosmic ray came in, it knocked out particles, and those particles had enough energy to move through ice higher at a faster speed than light moves through ice. Does that make sense? Because the speed limit is light in a vacuum, not light in ice.
Okay.
That's the speed limit.
We're going to need to take a break, because I think my brain is going to explode.
It's incredible what we're using to find these things. So, you know what happens when something like that happens?
Yeah.
You would know this. You're into like, UAPs and all that kind of stuff. What happens when an object moves faster than the speed of sound?
Oh, I mean, you're supposed to get massive, you get those sounds, that sonic boom.
Sonic boom. Exactly. You get a sonic boom. Why?
It's too much friction.
Yeah, because the thingy is moving through the air faster than the speed of sound, and so you're creating this like disturbance. But like the what is sound? Sound is the rate at which the disturbance moves through air. So you're piercing through the air faster than the speed of sound, so you get this sonic boom. You get this cone shock wave.
Oh, does the same
We're creating a light shock wave.
A light boom!
A light boom.
Yo.
And that's what all these photomultiplier tubes, all these light detectors are catching.
The light boom. Here comes the boom!
Yeah.
Wait.
These light so all of those tunnels are catching the light booms from these high energy particles as they knock out other particles and create this churn. It's called Cherenkov radiation. Cherenkov radiation, after the Russian like physicist who like first proposed it and stuff like that and studied it.
I'm glad you made that connection, because that helped solidify it.
Yeah.
Because now I get
you've got a charged particle that's moving, so now the electromagnetic field can't move faster than like the thingy. So you're getting this like shock wave in the electromagnetic field, and that's creating a bunch of light. And that's what you're seeing, right? And so that's the way that IceCube, this giant observatory, observes cosmic rays.
Right. And what's the point here is like we are actively observing them.
Yes, and we're actively observing them. And what we'd want to do is we want to find these really, really big ones. Okay? And what IceCube has done right now, it has put constraints on how many of the big ones, of these really big ones, can be protons and not like heavier stuff.
Got it.
Because that's important.
So there's like a
ceiling. We want to figure out like how much of it is protons, how much of it is like helium nuclei, maybe nitrogen nuclei, maybe even higher gold nuclei, iron nuclei, right? And so they put a constraint on it. They said that like less than 70% are protons, which means that 30% have to be these higher nuclei, which now that's crazy because 30% are like these bigger nuclei.
Yeah,
how did they get that fast?
It's
already,
like it's already crazy that the proton was
is
going that
going
fast.
this fast.
And then now we're saying there's
other stuff
that's bigger.
Yeah.
And it's
that has the same energy. It's like, so
something is not right.
Yeah, and it's I mean, it's incredibly exciting, right? And IceCube I think is expanding, or at least it was before the budget cuts. Yeah. But they were supposed to do an IceCube 2.0.
Oh, they're gonna
which is like just bigger area,
yeah.
And so you get higher resolution.
Yep.
You get more resolution about where it came from. One of the cool things about IceCube is that it's actually more sensitive to stuff. Like, okay, here's the Earth, right? IceCube is on the bottom.
Yep.
It's more sensitive to stuff coming from up here than up here. Because here there's so much background. There's all sorts of random shit.
By the time it comes all the way through, there's
only the big stuff is going all the way through.
Filter.
Yeah. So the Earth acts like a filter. And so what IceCube is really doing, if you're on the North Pole, you're looking for stuff coming out of the ground. Isn't that kind of funny?
It is.
Like you're looking for particles coming out of the ground, like from the Earth, because the Earth has done the work of filtering.
And this is stuff coming from God knows how far away. And how far in the past.
Yeah. This is like outside our galaxy.
This is
like this is very much outside our galaxy.
Is this facility because Antarctica has a lot of complicated geopolitical issues.
Yeah. It's an international facility.
Okay, so
this is kind of like a CERN on Antarctica.
Makes sense.
Yeah. I mean, like Wisconsin Madison, I think was one of the first people to like create it, but like, and they had like tour like not that many, but and I think they partnered with other institutions as well. But now it's become this big effort, right? Because it's just like such a it's such a nice thing. Like the Earth has provided us with a giant ice sheet.
Right.
That basically doesn't move.
Right.
So,
that we can utilize as a sort of substrate by which to run these experiments. And so this is
I thought that was such a cool story.
This is really interesting because what's so funny is this facility has so many conspiracy theories about it.
Really? You've heard about it
in the UFO community because people are like,
no, it's just it's just tunnels.
The saucers are under the ice, and it's there so that they can.
No, I mean all of the data is publicly available.
I mean, this is why we operate from first principles.
Yeah. No, it's just a bunch of tunnels with like light detectors, and we're trying to look at light booms.
I will say. There was an interesting thing. I'll ask you about this next week about someone talking about neutrinos because so many people. Let me ask you this question: there's not that many neutrino detectors.
No,
on Earth.
No, there's a big one in Japan that's quite famous. There's one in I think South Dakota in the Black Hills that's quite famous. This one's a really good one. Yeah, not that many though.
The reason I bring this up is someone was making this hypothetical of if you're. I'm always talking about the intelligence agency. If you're an intelligence agency and you're looking for a communication channel that's extremely difficult to be able to intercept or hack, because there's not that many neutrino detectors, it is a medium by which, if you can figure out how to make it a controlled medium, it is a secure channel. Yeah, I'm not saying that's a thing, but a lot of people have talked about this.
I understand what you're saying. There's a patent. So one of my friends. Completely unrelated to the UAP community,
sure.
Right? Like one of my friends sent me like this patent that somebody from Johns Hopkins had made about like neutrino communication, where instead of using electricity, they use neutrinos. I was extremely skeptical, right? Because neutrinos are like incredibly hard to interact with.
I mean, we just talked about why.
Yeah, I mean, it's sense. Like, dude, like I kid you not, in the early days of like neutrino observations, there was like. There's a funny story of a PhD at Caltech who like wanted to like study neutrinos over his PhD, and he observed 7 neutrinos in like 6 years. So he had names for each neutrino that he's like. So like in his defense, he's like, so then I observed Fred, and then talks about Fred. Like, you know, it's like it was that hard. Now we're getting a lot more because these observatories are getting bigger and bigger.
Massive.
But like, you know, like to communicate, you would need something this big. And the other thing about neutrino communication is the background is so insane, right? Because like the sun, like we put our hands out right now. The sun is putting millions of neutrinos through us, through our hands right now, right? So like, it's tough. I don't think it's as simple as like a telephone.
No, I totally agree. It's just, it is interesting having both feeds of information.
Yeah.
In terms of sort of talking through this. So that story with you. So we went big, small. Mm-hmm. Now we're gonna go back to big, and we're talking about our potential interstellar Google Maps.
Mm-hmm.
And so this is New Horizons Images enables first, number one, numero uno, of interstellar navigation. By looking at the shifting stars in photos from New Horizons probe, astronomers have calculated its position in the galaxy. A technique, again, we always talk about tools and techniques and frameworks because they're not single use. You can expand and sort of get incredible amount of value from one key insight, like CRISPR in our last episode. This technique can be useful for interstellar missions. So if I'm trying to go to Alpha Centauri, I'm going to need navigation.
Yes, that's right. You're going to need navigation, and you can't rely on the Earth. Mm-hmm. That's the key here.
Right.
Alpha Centauri is 4 light years away. Okay, so if you're trying to beam back to Earth, being like, hey, where am I? You're going to have to wait 8 years, right? 4 years to get there, 4 years to get back.
There's so many movies. Every space movie touches on, we have this big ball that glows, or we have this projector hologram, and then you're going to use the star, the deep space, but navigation is fundamental to every space movie.
Yeah.
Because you got to know where you're going. Yeah. Because once you start going,
you got, and you know what's incredibly romantic to me about this particular story is we're navigating the same way that the big explorers navigated back during European colonization, but like they use the stars where don't fucking I didn't think of that, but like I was saying it, I was like, oh wait, no, those are that's the bad people. Anyways, but you know what I mean? It's like Magellan when he went around the world. Well, he died halfway, but when his ship went around the world, he used the stars to navigate.
Right.
And we're doing the same thing here at JPL and NASA, right?
It makes logical sense, right?
Yeah.
And we've talked about this where distances and frequency of different types of interaction, quasars, we talked about the vibration stuff earlier, allow for or the dimming rather, the great dimming, allow for a consistent reference point in order for us to be able to do stuff. But this is interesting because I guess, and tell me, help me understand, they were using existing imagery. This is another important point. We put this stuff on Earth or in orbit, and we point it out and we capture data.
Yeah.
And it's not like Twitter or the news where that data has a week of value, and then after the first week, all the possible insight that could be derived out of that has already been figured out.
No.
It doesn't work that way.
No. That data has timeless value.
Right.
There's always some massaging we can do to get some new insight, right? And that's what these guys are doing. Because so basically, like the New Horizons spacecraft is a spacecraft that was launched in 2006. It was the fastest thing that humanity has ever thrown out there into the cosmos. Okay,
so right now, Voyager 1 and 2.
Yeah. This thing was just on a straight shot to Pluto. Actually, first it was going to Jupiter, and then it was going to use a gravity assist by Jupiter to go straight to Pluto.
We watch space movies, so we know about the gravity assist.
And so you go around like that. Yeah, you use like Newton's laws basically to like give yourself a boost. And this thing is currently moving at 10,000 kilometers an hour. Okay. It's past Pluto, so it took 10 years to get to Pluto. Just imagine how far Pluto is.
That's
right?
Crazy.
It took these incredible shots of Pluto, and then now it's just out in the outer solar system.
On search for Planet 9.
Yeah, it's trying to find it. We'll see, right?
Yeah.
So usually when stuff like this goes out, like the Pioneer that's out into interstellar space, Voyager, which is out in interstellar space now, New Horizons. Usually, in order to figure out where you are, you basically beam back to Earth, and JPL has this thing. JPL, which is NASA's Jet Propulsion Lab out in Pasadena, maintains something called a Deep Space Network. Okay. So there's like an antenna dish that's like near Death Valley in California. There's one in Madrid. I forget where the third one is, but effectively it's at 120. It's like at a third of a circle around the Earth. So there's always a dish pointing in every direction.
You know what scene we should insert here is that scene from Independence Day where Jeff Goldblum is talking about line of sight to the president, and he's saying the reason that they have this global communication network is because anyway
of a line of sight. But in this case, there's a line of sight to every part of the cosmos.
Yep.
Right. So you've got like Earth with like 3 beams that are going out in opposite directions. And so what you do is you point to Earth and you say, okay, how long did it take to get there? I know which way the satellite is pointing to an extremely high degree of accuracy. So I can then, within tens of meters, resolve where I am.
Which is pretty good if you're close.
Yeah.
But gets increasingly not as good if you're far. Is
Yeah.
that kind of the point?
That's kind
Like,
of the point.
it's not-
If we're trying to do this for
real, right.
we're trying to go to the stars, we can't be waiting. Like even New Horizons probably has to wait like several hours, right, to get that information.
Yeah.
Right?
We don't
If
have
we're trying to navigate,
right.
not just like coast, which right now New Horizons is coasting.
It's just moving like
but if
this.
we're trying to navigate, what we're going to have to do is update our location as we're going through our journey.
Right.
And so what these guys did was they looked at where, so as you're moving, right, we always talk about on this podcast how we're stuck on Earth.
Yep.
Well, these guys aren't, right? These guys are not stuck on Earth.
Yeah.
They're moving through the cosmos. They're now in the interstellar medium, away from the sun's influence. And so to them, the positions of the stars are slightly different.
Right.
Does that make sense?
Yeah, because we're moving at some incredible speed as a system.
Yeah.
In a direction.
Yeah, in some direction, but they're moving
moving
this
this
way.
way.
And now the background looks different because they're from a different vantage point.
right.
And by looking at that vantage point and our vantage point and taking those pictures exactly, we can now resolve where they are, right? Because it can only look like that from one spot. And so we know where that one spot is.
That makes total sense.
And that's what this thing did.
Okay, got it. So
Right?
it is creating the next sort of instead of just looking back at Earth as a single point of reference to understand your position in this larger vastness of space. We are now using both that reference point and the reference point.
No, this one doesn't even use the Earth.
Use Earth.
It's just that.
It just you because we know.
Yeah.
And so we can back calculate from just the snapshot of the sky.
Exactly.
Which has an orientation or like a frame
Yeah.
that allows us to be like, oh.
Yeah,
look,
we're from there.
Over there's the Hollywood sign. Over there's Sunset Boulevard. Over there's Venice Beach.
Exactly, which means I must be here.
here.
Yeah, exactly. Okay. And the camera on New Horizons was not meant for this kind of stuff. So the air bar is like pretty big.
Fair.
It's like an astronomical unit, like the orbit of the Earth. Okay. So not great, but it's about the principle.
Yes.
Right?
It's about
because
the first principle.
Exactly. It's about this is the first time they use that principle, Yeah, so I think it's a cool story because they use Proxima Centauri and Wolf 359, which are very close stars. They figured out where they were in relation to the background, and then they did the back calculation.
I mean, this is
something we're going to use later, right?
I was going to say,
when we go to the stars, this is how we do it.
We upgrade the cameras so we get higher resolution, which will then bring that one that error bar down.
Yeah.
Right. And when you get that error bar down, I mean, is there a theoretical situation here where on platform, like on the New Horizons 2.0, it can get I'm getting in the weeds. It can get some sort of asynchronous update from our mapping of the whole universe, right? Like happening in the background, but it can be capturing live imagery, and doing a calculation in real time because we're sort of feeding it this background algorithm in like.
Totally.
You know
I mean, it could. Well, How I would design it
Yeah,
is
yeah.
how I would design it is I would have a computer that would already have the information
Yep.
on where the relevant stars are,
Yes.
and then use that to then just locally make
make-
the
right.
make the
You can
the
have
calculation.
you can have the
right?
LLM on your local machine.
Yeah.
You don't need to go to the cloud.
Although I don't want to hallucinate, and this is an easy enough problem where I could just like brute force it.
Fair.
Like I don't need a neural network here.
But I think this is actually an important insight, though.
I might need a neural network to actually identify the dots, but once I have
Yeah,
identified the
the
dots,
dots.
right? Because identifying dots is really good, like
Yeah,
image
yeah.
recognition,
Yeah, yeah, yeah.
in terms of like object recognition
yeah,
stuff. But
yeah.
like once I have the dots, then it's just physics, right, and geometry.
This I think is really important though because it allows untethered interstellar navigation.
Yes, exactly.
Like that's like the
That's the key.
That's the key.
That's the key. Like I don't want to depend on the Earth, which
anything.
might be like very far away at some point.
Which also means you can imagine, right, that you have, light sails, like a fleet of light sails
Yeah.
or whatever that go out that have their own onboard system like you described, but also because if you send a bunch of them directionally in like a close proximity, but not, over there, they could also information share,
Yeah.
right, in their local context.
Oh yeah, and then
over
like
there.
do like a hive mind type of thing.
Right, where they
Quorum
sort of-
sensing.
Right.
Yeah.
The fleet learning, the same way that Tesla
Yeah.
learns to do self-driving. I just, what I'm trying to do is like really hone in on the import of like, it's the technical insight and what it unlocks.
Yeah.
Is a totally different, those games like Age of Empire or Civilizations.
Yeah, dude,
Where
I
they have the
played those
technology,
all the time.
they have the technology tree.
Yes.
And the choices you make unlock different
That's
paths.
exactly, dude. Yes, you're on it.
This is like why this kind of stuff, because now we have all of these 5,200 new doors
to open, yeah.
that if we had not made that kind of fundamental insight, which seems at this point, because we don't invest money in these things and like we don't have wonder anymore and all that stuff.
Yeah.
But like it has interesting implications. That being able to have untethered navigation. Like imagine having Google Maps offline.
Yeah, just offline. Yeah,
But-
but that can like update
they-
based on
the-
like cameras around your car.
Like that's
Right? That's kinda cool.
That's great. 'Cause
Yeah.
I've been in my car with no service.
Yeah.
Several times.
Yeah, but if your computer just had the Earth memorized,
Right.
right, and then like just looked around with all the cameras
Yeah.
and been like, oh, I know that mountain,
yeah,
and been like, oh, you're here.
I
Right.
mean, I think that's incredible.
Yeah. I think it's a really cool concept. Yeah. And it's like
again-
the obvious thing to do, but like somebody's got to do it. And New Horizons is a great probe because the camera's still working. It's like in good condition, right? Voyager's like barely holding on. Like it launched in the 70s. It's like, bro, just like I'll tell you I'm alive and that's it. Don't ask me to.
And again, there is a delta between where we are now and like it being applied in a
Yeah,
kind of
yeah.
way.
But somebody's got to make that first
we
leap.
have to start somewhere.
Yeah.
We all get fried chicken, chicken wings, burgers, pizza. Someone had to do it first.
Yeah.
And so that's why a lot of these stories are so important. We have reached the point in the show, Mystery Box, where
Mystery box time.
Krishna is going to bring forth a story of the week, that I know nothing about.
Yeah.
And this week, it's going to be
About woo woo.
mind
body, woo woo.
We
Yeah,
love,
I gave you that little preview, right? Mind, body, woo woo.
As LA residents, we're big fans of the mind, body, woo woo.
Yeah, mind, body, woo woo. This one's real. Okay, so this is a story that involves brain scans,
Okay.
blood tests,
Mm-hmm.
and Google's Oculus, the VR system.
It sounds like a party I don't want to go to.
Yeah, yeah. I think I've been to one of those parties, and it was not fun. No, but fundamentally, let me ask a question. Okay.
Okay.
When you get sick or when you get exposed to a pathogen, how does your body respond? There's an immune response.
Yeah, I get
right?
sweaty. I get a fever.
Yeah, you get a fever. Your
shivers.
your immune system goes up. Your first responders in the immune system
Yep.
are like, okay, I'm gonna start attacking whoever's coming in, right? What if you just thought that you were getting sick?
Wait a minute. Okay. This is funny.
Yeah.
Because
Not even what if you just thought that you were getting sick? What if you just saw a sick person near you.
Okay.
It turns out the body has the same response. The immune system starts working even if you see a sick person near you.
Bro.
That's it's crazy.
This makes so much sense.
Really?
This is yes. I want it. This is again mystery box. So
Okay, go on.
no. So my wife and I tell her this all the time.
Yeah.
When I fly, I've gotten sick almost every time I've flown, like in the last 6 to 12 months, which is brand new for me. And in one of the recent times I flew out, I told her, I was like, I'm not getting sick.
Yeah.
And I'm like, I'm just going to think that I'm not going to get sick and I won't get sick.
Okay.
And it has worked. Since I've started saying that. But this idea of me making eye contact with someone with the sniffles,
And then your immune system responding.
the like background system being like, oh,
Yeah, that's what this is.
but it makes sense though.
That's what this is. I mean, it kind of makes sense.
It's a survival mechanism.
No, that's exactly what the authors of this paper are arguing. But to me, what's incredible is like your nervous system is like prying your immune system. You know what I mean? Like it's this like this connection between mind and body that's like so real. So let me describe to you before we get into it, okay?
Go ahead.
Let me describe to you what the experiment was.
Yes.
And then how they concluded all this
This
stuff
is
because
great.
it's
I love mystery
It's pretty
box.
interesting. Okay. So they got these volunteers, okay? Split them up into two groups. Okay. First group, you had these volunteers put on VR headsets, okay? These are virtual reality cuz ethically, if you want to do this kind of experiment, you can't like literally expose people to sick people. All right. Okay. So let's get past that. What do? You put on the Google's Oculus. Okay. And you got one group that has like
Facebook's Oculus.
like people with like rashes and like sniffles and like coughs. They approach in this virtual reality world. Okay. And the other group just has like normal people approach, okay? And then there's a third group that gets flu shots, okay? So the first two groups, the Oculus group that gets the rashes and the coughs, they're being exposed to visual stimuli of sick people. The second group in the Oculus cohort, they get exposed to normal people. And then the third group get exposed to real pathogens, right? Because a flu shot is like some kind of like sort of dead virus, but it's still a virus and it's going to create an immune response. That's the whole point of a vaccine. Okay, so what they found was that the group that had the Oculus like VR experience with the rashes and the coughs had the same kind of immune response as the people who had the vaccine.
Get the F out of here.
That's not all, okay? So they went a little bit further and they actually did EEG, which is electroencephalography, like on their brains, where you attach a bunch of electrodes to the skull to try to see like what brain areas are active. And they also did MRI imaging on the brain to see which brain areas became active during that time. And the part of the brain that became active was the frontal and the parietal cortex, like up here, which has to do with something called it's like a preemptive response. It's the part of the body that like deals with the stuff that is near you.
Yeah.
Like this sense of like self and personal space.
Yeah.
Okay?
Your little aura bubble.
Yes, your aura bubble. It activated the peripersonal space system. Okay? So now you've got this like mechanistic understanding, right? Where it's like, okay, I see sick people. The part of my brain that deals with like my body and like the immediate surroundings of my body are being triggered, and then
like
that
that
triggers
thing.
and that triggers the lymphatic system and the immune system to then release these things called ILCs, which are innate lymphoid cells, which are like the first responders.
Yeah.
Right. So then when you did the blood tests on the patients, on the volunteers, you get like the same level of these ILCs that people with like it's so weird.
This is
It's like a conscious observation triggered like an immune response.
The way I was thinking about it in my head is like the immune system has akin to giving a computer vision, right? It's
Yeah.
it's like giving the immune system access.
Yeah.
to
I mean,
like,
it always had this, but this is the first time we measured it, right?
Like it can.
And it's like, and yeah, at some point, it's like, yeah, of course the brain, of course there's like some subconscious pathway, right?
Sure.
That is gonna see that,
Sure.
and then trigger the immune system.
Yeah.
Right. Just like how like things are triggered by stress and things are triggered by, but it's a very, I like the way that they did the experiment.
I was literally
Right.
gonna say because
With the VR
because
and with the.
I think that's the interesting thing. It's like even in this manufactured because you could argue like if it's human to human, it's real life, right? There is something that is subtly different
Yeah.
about like the real world interaction versus an abstraction via the VR headset. What's almost most fascinating is that it still activates.
Yeah. Yeah,
in that
like
context.
obviously they knew they were in Oculus.
Right.
Right?
Like they were
Consciously aware that they're in a
this is
VR
not real.
system, but
Right.
like still the subconscious part of the pathway
Yep.
was like,
don't
that
know.
person's got a rash. Like, you know, like whatever neural network is working in the background, identifying like sick people.
You know when people say, "I feel like I'm getting," like they get that feeling,
Yeah.
that they feel like they know they're about to get sick. It's kind of like this interaction.
Yeah,
between
and so
these two systems.
yeah, and like, yeah,
It's
cool.
that's actually really, really cool.
Yeah.
The experimental design is interesting because it sort of creates one interesting degree of separation, like we just talked about, and the fact that the system still has similar activation levels.
Yeah,
With the digital. I mean, there's so many like weird implications of that because you could probably extrapolate. There's a lot of people who've had concerns about like digital companions and VR and its ability to affect your like emotional.
yeah, but
state.
this is going even beyond
Beyond
that. It's
that.
not even. It's like the subconscious immune system thing
Right.
that I didn't even know I could control. But like visible stimuli is now controlling it.
Which sort of brings up this like issue of like, okay, so that means, right, like all of our forms of visual consumption, regardless of whether it's real
Like
life
on the phone.
or digital,
Yeah.
is having this, at least in this context.
Wow, I didn't even think about
You
that.
know what I'm saying? Like that implications of that are actually kind of crazy.
That is kind of crazy. Shit.
Yeah, like, which is why it's interesting they did VR with it for ethical reasons.
Yeah.
But
No, you're right. It's like,
where does that stop?
yeah,
right?
it's like the content that I consume digitally. How much is that shaping like a subconscious
Yes.
part of me, like my body?
Yes.
More than my mind at this point, right?
You would maybe make the argument that with VR, because it more closely mimics your normal perception.
Yeah, I mean that's the point.
That probably has a higher
Yeah.
whatever. Like
Yes,
impact.
yes. But it's not a steep cutoff, right? There's gonna be
Some
Yeah.
and so the question is, what is the delta between the VR context
Damn.
versus the anyway? I didn't
even think about that, dude.
This is why we love Mystery Box.
That's crazy.
What a great story, dude.
Yeah, I thought it was.
That's a
I saw
great
this. I
story.
was like, oh, dude, Lester's gonna love this.
Oh my god,
Yeah.
I hate being sick. It's the worst thing ever.
Yeah.
However, it is good to know, don't look at the sick people. Don't look at the sick people.
Yeah. Just don't look at him, dude.
It's like that. What is that? It's not like there's those movies.
Well, but then your immune system won't get primed, and then maybe you will actually get sick. So
this
I
is the
don't
whole,
even know.
Yeah, look, this is
Chicken and egg.
Damned if you do, damned if you
Yeah.
don't. With that, we are going to wrap up this week's episode of From First Principles. I am your host again, Lester Nare, joined by my co-host and the smartest person I know, as well as our resident PhD, Krishna.
You need
Chowdhury.
to get more friends, mate.
We'll see you guys next week.
Peace.